know each other, Niall. So if I'm not wrong, you've done your PhD in UCL.
Yeah.
And now you're at ENS.
I'm in the process of moving back to UCL at the moment.
Okay. So you were at ENS, very close to us.
Yes.
And today you're going to talk about CMB and method to get the CMB.
Yes, exactly. Yeah.
Thank you very much.
Can you see that?
Yes.
Okay, perfect. Okay. Please do shout out if you have any questions, or just call out, and I'll be happy to answer them on the fly, as it were, but I can't see necessarily the chat at the moment. So I'm happy to take questions. And this is work on CMB B-mode inference with a single frequency, but the real stepping stone, or the real new path here, is using realistic foregrounds with a single training image. So this makes this approach now feasible for actual data. This way of doing foreground removal and particularly inference beyond what you would usually be able to get. So this is work with François Boulanger, Ben Van Delt, a former student, Bruno Regaldo Sambranca, Owen Alice, and François Levrier. So this is the setup. This is the kind of final plot. And then I'll go through and explain how what the different steps were that got us to this point. So this is, for example, a patch of data, in particular B-mode polarization data. As it would be observed, this is simulated. And what we're able to get from this, using our approach, is the mean of the posterior distribution per pixel. So we're doing this Bayesian inference at pixel level, and also the posterior marginal variance as well. So we're able to quantify the posterior probability of each individual pixel from this patch of B-mode data using no frequency information whatsoever. So the steps here. So the first step is this approach, which is likelihood-free inference, and in particular, how we're able to do this likelihood-free inference in very high dimension. Then I'll talk about our realistic forward model, how we're able to generate realistic synthesis of the foreground, the B-mode foregrounds from dust in a way that is realistic enough to do this method. And we're able to do that efficiently and fast. And finally, I'll talk about how we actually validate this posterior distribution. How do we know that when I say this is a posterior distribution, this is the posterior probability of my pixels, how do you know if that's true or not? How do you know that that what we're seeing here is really the posterior probability? And that is just because I say this is Bayesian doesn't mean it is Bayesian. That needs to be tested as well. So first of all, high dimensional likelihood-free inference. And in particular, a new method called moment networks that Ben Van Delt and I developed. So in typical parameter inference, we have our possible data D. So in the case I've just spoken about, our data is a B-mode map, or in particular, it's a general E B-mode map or QU map for polarization. And our unknown parameters are our signal. And in the example we've talked about here, those unknown parameters are actually every single pixel within that underlying pure B-mode map that we don't know when we're trying to infer. And of course, the posterior probability. Can you see my mouse, by the way?
Nope.
Nope. Okay. Oh, no, that doesn't work. How about now?
Nope.
Ah, okay. What about now?
Still not.
Okay, all right. Well, I'll give up. Okay, so the thing on the left is the posterior probability for that signal given our data, and it's related to the likelihood and the prior, where the likelihood is this sampling distribution probability of the data given the signal evaluated for the actual data we observed. So in likelihood-free inference, we don't actually know the form of this likelihood function. So typically people might assume this is Gaussian for all sorts of reasons, but there are many situations we know this is just not true. So likelihood-free inference is not that we're not thinking of the concept of a likelihood. It's more that we don't know how to write down analytically the form for the likelihood. In this case, for the CMB foregrounds, it's extremely non-Gaussian, and we don't know a priori what the form of that likelihood is. So instead, what likelihood-free inference is taking simulations of your data and a label of the true signal. So these don't have to be simulations. They could be any sampling of your data labeled by the true signal. And typically we use machine learning methods to then estimate the form of this probability density P of D given S. So we have our DI, simulated data vector summary statistics. So these Ds have all of the effects that one might observe. It includes all the noise, all the masks, all of those kind of things. So they're meant to be as realistic as possible. And what's happening when you generate a simulated mock data vector is that you're drawing these DIs from the distribution P of D given SI, where SI is the label that you know. And every time you run a simulation, you're drawing these D data vectors from this probability distribution, P of D given S. And the point of likelihood-free inference is saying, well, I have now all of these datas drawn from this distribution, and I have the labels S. What I can do is, from this set of points, is I can now estimate what density those were drawn from. So it's a density estimation problem in this particular case, but it doesn't have to be. So for example, if you're unlucky, you could have your data in a one-dimensional case. You have one data point and one parameter you're trying to infer. Your data might have this form here, where the data and this, if you plotted your simulated data point D and its label S, you might get this shape. So the point of likelihood-free inference is estimating a functional form for this shape so that when you take your actual data that you've observed from the sky, you can work out the posterior probability for your signal. So estimating this density, you might get the probability of D given S. So that's then your likelihood that you can evaluate for the real data. And a typical way of doing this is with a normalizing flow in machine learning, where you take, you try and find a mapping, a bijection between a known distribution, like a Gaussian you can see on the left, that transforms your points on the right, your simulations, your data and signal simulations, into the known distribution. So this is how a normalizing flow works, as a series of transformations that transform you from a Gaussian to your target. So once you have this, you now have a way of transforming a density you do know, which is a Gaussian, to your actual sampling distribution, which would then give you your likelihood. So without ever writing down a likelihood, but only by simulating, you're able to find what the functional form is for the likelihood that you did not know. So one particular implementation of this in a paper with me, Justin Outhing, and Francois Lenus is applying this approach to data from the dark energy survey, in particular the SV data. And here you can see you can see how many? 4 different posterior distributions, where in not a single one of these posterior distributions, so the data is the same, but the data is slightly different in each one. But in none of these posterior distributions, for this S8 amplitude parameter from the amplitude of fluctuations, in none of these have we ever written down a form for the likelihood. So we take our data from the dark energy survey, we form summary statistics. So in these cases, there's the power spectrum, the orange dashed line. The solid blue line is the power spectrum across the count of the number of peaks in the map generated from the data. And then the 2 final ones, the purple dashed line and the red dashed dot line, are convolutional neural networks using 2 different methods to compress that data first instead of using these power spectrum constructed statistics. So this is all to say that here we have 4 different possible summary statistics, and we've simulated this data. We've varied this cosmological parameter S8 and some other cosmological parameters. We use this approach of normalizing flows to then, from that simulated data, give us the form for our likelihood, such that when then we take the actual data, we just plug that our actual data into our learned likelihoods, and that gives us now the actual likelihood for our data, and we apply it to a prior, and we get our posterior distribution. So the point here is that we've never written down a likelihood, so we've able to skip lots of assumptions that usually get made in these kind of analysis about the Gaussianity of the noise, where usually it's not actually Gaussian, the Gaussianity of the signal, where usually it's not Gaussian, the actual density field of the universe is highly non-Gaussian, and things like masks in the data and shot noise as well, which all contribute non-Gaussianity. We haven't had to assume any of that when we wrote down our likelihood. Instead, we've just simulated all of those things in a forward model and learned what the form for that likelihood was in the form of a normalizing flow. So that's the kind of standard approach to this likelihood-free inference, which is also known as simulation-based inference, with a few parameters in the case of this dark energy survey example. Does anyone have any questions on this bit before I move on? I'll take that as a no. So we have our standard approach now. So this is the standard approach to likelihood-free inference with normalizing flows for a few parameters. So the problem with applying this to what we've just spoken about is that in the previous example, I had 2 parameters. Let's say I had my S8 or sigma 8 parameter, which gives me the amplitude of fluctuations in the universe, and I had my omega matter density parameter. So 2 parameters. So I was able to learn a normalizing flow in effectively 4 dimensions, because you have 2 parameters, and then the compressed data has a minimum dimension of 2. Because I have 2 parameters. So that's the minimum number of dimensions I can get away with for my density estimation. So doing density estimation in 4 dimensions is not so bad. It's perfectly possible. But if you try and do density estimation for a map level, for the example I showed you at the very start, there are 256 squared pixels. So that means my parameter space is 256 squared dimensional. And for actual data, we're talking about millions of dimensional parameter spaces if we consider each pixel as a parameter. So doing a density estimation in 1,000,000 dimensions is completely impossible. You suffer terribly from the curse of dimensionality. So this approach here that I developed with Ben van Delt, oops, sorry, I've lost my mouse, is an approach that sidesteps the density estimation approach and directly targets the posterior distributions of the marginal posterior for each pixel, and also pairs of pixels as well. So we say we can't estimate the full posterior distribution for millions of dimensions, but we can calculate the posterior distribution for each parameter and pairs of parameters, because that's all you ever plot at the end of an analysis anyway, because a human cannot conceive of a 1,000,000 dimensional parameter space. And it's very difficult even to plot a 3-dimensional posterior distribution. In fact, you plot the marginals for each parameter, the marginal posterior distribution for each parameter, and the marginals for each pair of parameters. So you get these kind of contour plots or banana plots. So this is what the moment network attempts to do. So it sidesteps density estimation, but still is able to find the final posterior distribution. So this moment network approach is a hierarchy of networks where we have we can have as many as we want, but we have, in the case I'm going to show, 2 networks in a hierarchy. So the first network, this F here, so you can see, will find for us the mean of the posterior distribution for each parameter. So we have a network F, and it takes in data, and we have our simulated data and its label of the true signal. And providing that the true signal has been drawn from a prior, the prior we want to use. So we draw some set of signals from a prior distribution. We then draw some mock data, generate some mock data based on that signal. So we've now drawn from the sampling distribution. So our data and signals are now distributed according to P of D and S, as you can see here. So you have P of D and S. So when a neural network F minimizes a loss, it's minimizing averaging over that joint distribution. So what this means is if I find F of D that minimizes my function of my data that minimizes this squared loss over my training data, which are drawn from the correct distributions, then what that means is that this F function, once trained, will be equal to the posterior mean for the data it is given. So this is a standard result going back to Jaynes and even potentially Laplace, that if you minimize a square loss over this distribution, then this function F will be equal to the posterior mean for your signal. So already anyone doing machine learning with a squared loss, providing that you have really drawn your training data from the prior and then the sampling distribution, or a hierarchy of a Bayesian hierarchical model of anything like that, then what you're doing is estimating the mean of your posterior distribution for your signal. So the point of the moment network is then we go to a next level. We say, well, if I can estimate my posterior mean, I can actually construct a loss on a second network that then will give me my variance of my posterior distribution for each of these pixels, which will now give me an uncertainty quantification. So now I've trained my first network F, and so that's called F fixed in the second layer, second level of the hierarchy. So F is now giving me my posterior mean. So if I take all my signals in my training data, subtract the posterior mean for the associated data, square that, I then find a different function G that tries to output this quantity on the left, subject to a squared loss again. And again, if this squared loss is minimized over the joint distribution of the data and the signal, then what G will be is the posterior mean of the thing in there, which ends up just being the posterior variance, effectively. So what G is now is an estimate of the posterior variance. And we don't have to do this just per pixel, we can do it for pairs of pixels. So we can say, given all of the data, I can make G be the posterior covariance between pixel A and pixel B, for example. So I'm able to construct an estimate of the posterior distribution for a large number of pixels without fully estimating the high dimensional posterior distribution. First, we directly go to the thing that we actually care about, which is the mean and the variance of our posterior distribution. And of course, we could calculate other moments of that marginal distribution. So what we have now is a tool that if we're able to generate signals from the prior, data from a realistic simulation or realistic synthesis of the data, then now I'm able, if I have all of that apparatus, I can come up with a moment network that will give me mean and variance estimates for my posterior distribution for some new data that we're yet to observe. Does anyone have any, oh, sorry, I've lost my thing. Does anyone have any questions at that point? Nope, okay. So we have this inference framework now. So we're able to calculate posterior estimates from our large set of training data if we can generate that training data. Okay. So this is now where a different aspect, which is how we generate these realistic CMB foregrounds. So we want a generative model for the data. I want to be able to synthesize signals. The signals are easy because we assume it's Gaussian, the CMB, the underlying CMB signal. But the foreground dust is extremely difficult to simulate. We don't have much training data from the sky that's low noise and pure dust. And running simulations of the foreground dust is extremely difficult. So we want a method where we can generate new realizations of the foregrounds so we can create realistic training data for our moment network. So how do we go about doing that? And in particular, what we're able to do is come up with a generative model for our foregrounds that only takes in one training image, which is extremely useful in this case because we're really data poor when it comes to the CMB dust foregrounds. So the approach is wavelet phase harmonics. So we take an input image. In this case, for this example, this is an input image of the cosmic web, just as an example here. So if we have some input image, we apply two different wavelet convolutions with different wavelet scales. And if you do this, you end up with an amplitude and a phase for each scale. And the step of wavelet phase harmonics is that you can then spin up the phase of one of those signals. And now what happens is that if you take correlations between such images, different phase rotations and different wavelet filter sizes, you end up with a set of statistics called phi of your input image, which are a very good characterization of the textures within that image. Or more particularly, phi, these covariance between these phase harmonics, ends up being a good model, or it encapsulates the model for the original generative process that we don't know, the input image. So what we can do is we can take a new input image, measure these wavelet phase harmonic statistics, and then with those wavelet phase harmonic statistics, you can synthesize a whole new set of images. So if we have a generative model for, so if we want to generate new realizations of data, so we have this simulated Q map here from the dust. So this is our polarization Q map from the CMB for a bicep-like size patch. And from that, we can generate new realizations of this original image. You can see A, B, and C, and new realizations of the original image without actually themselves being just copies of the original image. So, and we do this by finding a new synthesized image that minimizes the difference between the measured phase harmonics of our new image and the phase harmonics of our target image. So using this process, we can synthesize lots of new images which have the same phase harmonics as our target image. And these new images are good synthesis of the original process. So we're able to generate new realizations of the foregrounds without running any more simulations. So now I'm talking about the steps that are involved in generating our training data from our sampling distribution. So the foregrounds we need to be able to generate. So this is this step. In what I'm going to skip over a lot of steps where we try and match the foregrounds amplitude and other properties to the uncertainties in those properties from the Planck data. And the signals, the underlying CMB signals, are drawn from the prior given by the Planck data as well. So our prior on our cosmological parameters is our Planck posterior. From those cosmological parameters, we generate new maps, CMB maps, and then we can add them together to generate our mock data. So these are the power spectrum of just two random examples, or not random, these are two examples of our training data. So in the first case, validation data A, you can see the power spectrum of the foreground and the power spectrum of the signal, and the power spectrum of the signal about L of 1000, you can see that the signal is dominating. In the second example, because we have uncertainty in the foregrounds and the signals themselves are drawn from some distribution, then the foregrounds dominate in this particular example. So this is to show that when we do this training, we are implicitly marginalizing over our uncertainty in lots of different quantities. And in particular, we're not fixing ourselves to one set of cosmological parameters or one particular model for the amplitude of the foreground. So now we plug this into our moment network and we're able to generate estimates for our underlying signal that we want to get. So on the left, you can see the truth, our B-mode true map. And in the middle, you can see some B-mode data using a simulation that we haven't used to synthesize our training data. So this is now with a completely new, unseen simulation of the foregrounds. So all our moment network sees is just the B-mode data. It doesn't see the truth, and it's able to generate this posterior mean here. So it's able to come up with an estimate of the posterior mean of each pixel value. So you might look at this and think, well, there's some artifacts going on here, that in the bottom, for example, our power is suppressed. But actually, this is exactly what we would want to happen for this particular case. If the B-mode data is very high in amplitude and obscuring the underlying signal, then the posterior mean should get pushed closer to the value, to the mean prior, which is 0 in this case. So actually, we're seeing exactly what you would expect, that when you have a lot of foregrounds, as you do in the bottom left, you can see a lot of foreground power. Then in the posterior mean, then we end up with a suppression in the power of the posterior mean. But because we end up with this suppression in the power of the posterior mean, because we have a lot of uncertainty coming from the data, then we should also see that represented in our uncertainty. And we can, if we look at the posterior variance. But before we go and look at the posterior variance, I want to say, well, I know I've been saying, well, we mustn't think of this as a cleaned map. It's the mean of the posterior. So this is why there are these things that look like artifacts but aren't. But if we just want to, first of all, see how well we have done in recovering some signal, we can treat our posterior mean like a cleaned foreground map. And we can now measure the signal to noise within that posterior mean map. And this is what we get. So this is the power spectrum of the truth divided by the power spectrum of the residual between the data and the truth, and the residual, that's the blue dashed line, and the residual between the posterior mean and the truth. So this is effectively a signal to noise in harmonic space. And what we can see is that in the case of the data, there's only signal to noise greater than 1 for around L of 1,000. But in our posterior mean, we end up with much higher signal to noise at those scales. So we're really recovering signal that was previously obscured by the foregrounds. So the foreground removal aspect is really working. We're removing foregrounds and uncovering real signals. Okay, so now posterior validation. So at the very start, I showed you the posterior, I showed you the data, the mean of the posterior per pixel, and then the variance per pixel, the marginal variance per pixel. And I said, well, just because we say we're Bayesian doesn't mean we are. How do we test this posterior distribution? So before I show you what test we do, I want to show you an example of what the wrong answer would look like. So you can see a case where it goes wrong and therefore see what we're doing right when it happens. So let's have a model where I have a model now where the signal is the CMB and my foreground is Gaussian, but my foregrounds are also Gaussian. And in this particular case, I can solve it analytically. I can say, what's the probability of my signal given my observed data? And I can come up with the mean and variance of that. So I solve this analytically. So I plug in the mock simulated data into that analytic Gaussian model, and I get this result here. So if you want to look at this for a few moments, you can, your eye might be drawn to the high power in the residuals around the bottom of this image and in other places as well. So what's going on here? Well, what should be happening, as I said earlier, is that when you have a lot of foreground, as you do in the bottom left area of the data, then your mean of your posterior distribution should get pushed towards 0. But what's happening here is that actually the posterior mean is adding power on those patches where there's a lot of uncertainty, which is the opposite of what should be happening. And this is because, of course, our naive Gaussian model is completely wrong. The foregrounds are extremely non-Gaussian. And what's worse is that in this naive Gaussian model, because everything's stationary and isotropic, the posterior variance will be the same for every single pixel, which is, of course, not representing what's actually going on. The posterior variance should be high where the foregrounds are dominating, and the posterior mean should be pushed towards 0 where those are dominating as well. But the opposite is happening here, that the posterior mean has higher power in those patches where we're most uncertain, which is completely wrong. And so we know that this is not happening in our case. So in our case, you have the data on the left, the posterior mean in the middle, where, as we saw before, where you have lots of foregrounds, the posterior mean gets pushed towards 0 because we're more uncertain. But at the same time in those areas, the posterior variance is getting pushed up. So we can see on the right that we're actually the darker patches where we have more uncertainty, where there's more variance. So it's doing the right thing, by eye at least. So from that point of view, it's doing the right thing in comparison to the naive case. But then we can ask ourselves, is there a way of quantifying how well this is doing, not just saying, well, by eye, it's doing exactly what we expect. So this is the test we do. We take the rescaled residuals. So for every pixel in our image, we take the mean posterior value of that pixel, and we subtract the true pixel value. Again, this is happening on the validation data, not on the synthesized data. So we took, so this is also going to be a test of not just the moment network, but also how well our synthesis is recreating the foregrounds realistically. So we take our posterior mean, our true pixel values, subtract them, and then rescaled by the posterior variance coming out of our moment network. And if our moment network is doing the right thing, and if our foregrounds synthesized by a wavelet phase harmonics are realistic and representing the simulation sufficiently well, then these residuals will have mean 0 and standard deviation of 1. Okay, if all of those steps are working correctly. So this is the distribution for those residuals for our test case A, our realization A. And you can see it has mean 0 and standard deviation 1 almost precisely. And we've plotted here a normal distribution with mean 0, standard deviation 1 as comparison so you can see how well this is really doing. So for realization A, the fact that the mean is 0 and the standard deviation 1 is really telling us that our phase harmonic statistic synthesis from only one single training image, which is a different training image, was able to synthesize new dust foregrounds in polarization sufficiently well that when they were used in our likelihood-free inference framework and then applied to real data, then the result was perfect. So those syntheses are sufficiently good for this particular problem. And what it's also saying is that our moment network, trained on those synthesis and simulations of the real signal, the moment network is correctly estimating the mean of the posterior distribution and the variance in this extremely high dimensional space, which wouldn't have been able to be done if we were using a normalizing flow. So it's validated the synthesis and the moment network. And you might ask, well, this is just one particular example. How do you know it works on different examples? Well, I can show you 3 other examples where the histogram of our rescaled residuals has mean 0 and standard deviation 1, and it is matching extremely well. So for all of these cases, we know that the moment network is working and our synthesis are realistic for this problem. So I think I will end there and ask if there's any questions or discussions or disagreements anyone has. Thanks.
Thank you.
I have a question, if I may.
Sure.
In fact, you have distributed your foregrounds with some statistics, which is not Gaussian, but which was exactly the same, in fact. Is there some part of the sky where the statistics is completely different and you can use several statistics and may have several sigma and so on?
Yeah, so that's the current plan for when we're applying it to data, is that we would expect that rather than using one particular patch of the sky, you might use a few patches of the sky so that you encode the variation, some kind of intrinsic variation in statistics over the sky. And in particular, so we might assume that rotationally along the axis of the galactic plane, we might be, the statistics might be invariant in that direction. But we know that if you go to the pole, that the statistics are no longer stationary in that direction. So what you would additionally want to, because if you're at the top, you might be more CIB dominated, cosmic infrared background dominated, whereas if you're closer to the galactic plane, you'll be more dust dominated. So in fact, for the real data, we do want to sample along that axis as well. But as long as we sample along that axis and we're able to sample these statistics, we will then be able to just include those in the forward model, and that uncertainty will have been included in the analysis.
But there will be more uncertainty, in fact. It will increase the variance? Exactly,
yeah. So if in the forward model there's more variance in the mock data, that will propagate to more variance in the uncertainties in the pixels, and eventually more variance in the uncertainty in the cosmological parameters as well.
Okay, thank you.
I had a similar question. In fact, when you have a new realizations from the start, I mean from the first image, how do you know? I mean, how much the realization is dependent on the choice of this image? I mean, in terms of I don't know, the size, and the statistical distribution of your signal in this image.
Well, at least for this the size is fit by the data that you're going to observe. So if you're going to use BICEP, you will need a patch that is the size of BICEP.
Well, in fact, just to ask the question the other way around, my question was this: the motivation was, does it help you to restrict or to choose the size of the image of your observation? Do you see what I mean?
It shouldn't. It should be that depending on how you implement it, the more data you have, the better, because you'll be probing. You'll just have more modes within a given image. If the image is not stationary within that image, it might you might not want to treat that as one image. Imagine along the sky you have non-stationarity, that you're moving from the pole to the galactic plane. It would be better, as I said before, to sample many images along that line, and thus somehow have a model that includes that variation, than taking one big image that is not internally stationary. So does that answer the question?
Yeah. So basically, you don't have to do a full sky image. You can optimize the patches of observations that would be required to retrieve
exactly
the statistics that you're interested in.
And in fact, well, we can't do a full sky image because there's no full sky true dust map, and we don't. If we did it full sky, there'd be no data left for the CMB, because you'd have to split it somehow. But even if somehow we had a different universe where we could use the full sky data, we wouldn't want to anyway, just because as I said, it's not stationary. So what you would end up doing is you would end up measuring the phase harmonics of the full sky, which would give you a statistical model, which would, when it was used as a generator, would generate images that were isotropic on the sphere, but had the statistics averaged from the actual data. which we don't want to do.
Okay.
So in fact, we want a mixed model where some of the, in reality, if you were to do a full sky model, you would want to encode this mixture of variation within the model itself.
Okay. Any other questions? No? Okay. So thank you very much again. Thank you to everybody for attending, and see you next week for the next seminar.
Thank you. Bye-bye.
Bye.
Bye.